everybody, welcome. Welcome to Lecture 7. Today we have our portable Wi-Fi hotspot back again, so hopefully we won't have any additional technical snags. Today will be, I think, an interesting lecture for some of you, a challenging lecture for others of you, and hopefully an elucidating and useful lecture for all of you. We'll see. You have a reading assignment from Fujishiki's book, which has not changed since last Wednesday. And you also have a homework due, which is this coming Wednesday, and it is due at 11:45 p.m. electronically. And for those of you who've taken classes with me before, you know the drill. It has to be a PDF file. You upload it to this particular link, and it's pretty clear. Nobody has ever in the past had troubles with it, but it does have to be a PDF file. But like I said last time, you're more than welcome, if you prefer, to do it on paper first by hand and then take a picture of it with a clear, high-res, high-contrast camera, concatenate the JPEGs into a PDF file and upload that. That's perfectly fine. Okay. So today what we're going to do, we just briefly touched upon dual matroids last time. So what we're going to do is really talk about dual matroids, some other interesting sort of geometric properties of matroids that might hint at why some prefer to call them combinatorial geometries. And then hopefully we'll have enough time to finish all of the slides of today's lecture and actually end up with the relationship, the formal relationship between matroids and the greedy algorithm, which is pretty fundamental because that's actually going to connect us to ultimately the relationship between the greedy algorithm and submodular functions. So let's just do a little bit of review. And also, there are a couple of questions that came up at last lecture that I wanted to address in this review. So remember, we defined the system of distinct representatives, or equivalently as a transversal, as the following. You have a set system of some sort. You have V and script V, where script V is a set of subsets of V, and a system of distinct representatives is essentially a set of elements, a subset of regular V, or in other words, you have essentially a representative for each of the sets inside of script V. So then that's called a transversal, and essentially what we define it as essentially there being a bijection, and a bijection is such that for every T, so T is the transversal, so T is a subset of V, and T is transversal if essentially for every element, every X in T, this transversal, there's essentially a unique set that it's represented, which is V sub pi vi, which is the bijection. And so that everything makes things distinct. Now, what we wanted to do was understand why or when do transversals exist, and that led us to the famous theorem called Hall's theorem, which is actually studied quite a bit in graph theory. And basically, first of all, we defined this function V of j, which V of j, so j was a subscript of the index set, and so I, in some sense, can be seen as another ground set. So we have one ground set V, which corresponds to the left side nodes on a bipartite graph, and then another ground set I, which corresponds to the right-hand side nodes on a bipartite graph. And V of j, this thing here, basically is a mapping from subsets of j to subsets of I. Okay? And then Hall's theorem states that basically this set system has a transversal, or a system of distinct representatives, if and only if, this is an if and only if condition, for all index sets, for all subsets of I, we have the following quantity. Basically, the size of V of j, or the size of the neighbors. So remember, these are you can think of these as subsets of nodes on the right-hand side of the bipartite graph, and then the size of V of j is basically the size of the neighbor set on the left-hand side of the bipartite graph. The neighbors of essentially a set of indices on the right-hand side of the bipartite graph, and so the size of the neighbors has to be greater than or equal to the index set for all possible index sets. And we saw this particular picture. So here's a bipartite graph. These are the left nodes, in case anyone isn't shortened. And these are the right nodes on the right-hand side. And this is a particular transversal, where we chose in fact, we matched essentially all four indices. And then what we did is we actually generalized this to Rado's theorem in 1942. One thing I wanted to actually mention was last time I talked a little bit about Hassler-Whitney's paper from 1935, and there wasn't really that much work on matroids until the mid-50s. So Rado actually was in some sense an outlier and proved this theorem back in 1942. So that was something that actually did happen not too long after, 7 years after Whitney's original paper in 35. This theorem generalizes the previous theorem by saying that not only is there a transversal, but it's independent in the matroid. So you have essentially a matroid with a rank function, and you have a transversal which is independent if and only if the following condition is true. Now we can essentially recover the original theorem by taking the free matroid, where the rank of a set on the left is basically the size of the set, and that's a free matroid, and we immediately get back Rado's theorem. But basically we also get that it's independent in the matroid because why? Because of the properties of the rank. Because basically the rank of a set is less than or equal to the size of the set, right? So the rank of V of j is going to be less than or equal to the size of V of j. Right? But we're saying that the rank of V of j, which is something less than or equal to the size of V of j, so we basically, I think I can write this down, or maybe I even have this written somewhere, but V of j, we know we have this property. Let's move it over a little bit. And so that inequality is always true, right, because of the properties of the rank. And so therefore that implies the original theorem, the original Hall's theorem. Now, one person asked me, what's an application of Hall's theorem? I mean, there are actually quite a large number of applications, but here's one that might be near and dear to your hearts after you graduate and then start looking for a job. So basically the idea is that there's a set of jobs, I. So the right-hand set of nodes in the bipartite graph are a set of jobs, and the left-hand set of nodes are a set of applicants, which is basically you guys. And the question is, each applicant is qualified for some number of a set of jobs, and so basically the neighbors of a particular V correspond to the jobs that they're qualified for. And what you want to do, basically, is set this up in a bipartite graph and see whether or not it's possible, given a set of applicants V, for all jobs to be filled. And that's essentially what this is saying. So we wish all jobs to be filled. And that is my cell phone. Sorry. That will go on the permanent record. Anyway, this is a necessary and sufficient condition for all jobs to be filled. Okay. Now, the other thing, and which might be seen as an application of this, is the marriage theorem. Is anyone familiar with the marriage theorem? So basically, you've got a bipartite graph, and basically the idea is that you have people of two different types, maybe people of type left and people of type right. Let's do this. Let's do the politically correct version of the marriage theorem. So you have Republicans on the right and Democrats on the left. And the number of Democrats and Republicans is the same. And the edges between an individual Democrat and an individual Republican exists between that if they're compatible, if they're willing to talk to each other. And basically what you want to do is pair off the Republicans and the Democrats to go on and have little half Democrat, half Republican babies together or something. Okay, so basically you basically set this up as a bipartite graph. In this particular case, the number of nodes, the number of V and I is the same. So the left-hand side and the right-hand side is the same. And basically, Hall's theorem basically gives us the marriage theorem, whether or not it's possible for all pairs to be matched by, basically people with whom they're compatible with. Now, it's possible that this bipartite graph has no edges, which is probably the case in the current political climate, but that would basically show up. Basically, Hall's theorem will say, nope, a match is not impossible, right? Because the number of neighbors for any subset of indices would be 0 in that case, right? So, but that would be a trivial case. Hopefully, a more compatible and maybe useful and sort of a case that would lead to some sort of progress happening would be one where a match would occur. Okay, so basically this is the idea. Any questions on that? So those are some applications. Basically, it has to do with matchings, like the existence of matchings, or the existence of matchings, sort of semi-perfect matchings where the right-hand side is completely fulfilled. Okay. Now, what we proved was the polymatroidal transversal theorem, which was a little bit more general. And that was basically where we have a polymatroid function, f. And notice that there's a little bit of a question about, notice that we've changed this now to system of representatives. We've removed the words distinct. A system of representatives such that this is true. Okay? So it turns out that if we just set f to be the cardinality function, that's going to be a guarantee that the representatives are distinct, right? Because basically we're saying that the size of the corresponding set of representatives for the index set j has to be less than or equal to j, the size of j for all j, which basically means that every j has a unique match, right? Which means it's distinct. So we don't need to actually say distinct representatives up here. And similarly, if we were, for example, to use a matroid rank function there, then we would get back Radu's theorem. So basically what we're saying is that stuff is true, like I sort of outlined last time, if and only if this is true. And that's the general thing. And that's the version that we proved. So one can hopefully fairly easily see that this is the more general case. Now there's another, I should mention, another instance, another generalization of Radu's theorem by Lovas that was done in 1970, which I was going to mention, maybe I'll ask something about that on a problem set, but it's not compatible with this particular one. Or at least it's not compatible in a particular case. So, I mean, we also talked about transversals and bipartite matchings, which basically says that the transversals, the set of transversals correspond to the set of matchings, and that basically means that the set of matchings in a bipartite graph corresponds to a matroid. Okay, because we saw that transversals were matroids. That's this theorem here, this whole theorem. And we also talked about something that's fairly fundamental, which is the idea of a matroid isomorphism, which basically there's a mapping between the two ground sets such that all properties, like independence properties or circuit properties or base properties or anything, are preserved. And we talked about how one can, for example, ask questions like if you define a matrix on a field, like the reals or some field like the Galois field P for P is some prime or something, basically whether or not a given matroid is representable as a matrix defined on such a field. And so any such matroid is called representable. Or we can say it's something like F. Sometimes we say F representable. So we might say something like F representable. And the implication here is that the dimensionality is finite, so basically the length of the columns, the height of the matrix, if you will, is finite. And if it's representable, if it's F representable, it means that there's some dimensionality of the matrix such that that matroid can be represented where all elements of the matrix are members of the field, and all linear combinations, all coefficients are also members of the field. Okay. And that's a really important thing because I think last time I sort of conflated a little bit. So we talked about, for example, that transversals are very flexible, but we saw that all transversal matroids were F representable, but we also saw that there were matrix matroids that were not transversals. Now the question was, and I can't remember if I answered this or not, do you think that there are matroids that are not F representable for any F? So let me just ask that question again, in case I asked it and you answered it already, but let me ask it again. Do you think, just intuitively, that there are matroids that basically satisfy any of the definitions of the matroid that we've defined that might not be F representable for any field? Assuming finite dimension, of course. Raise your hand if you think matrices can do everything. Raise your hand if you think that matrices can't do everything. Okay, so the majority is right in this particular case. And for the non-voters, every vote counts, right? because you could have switched the truth of that statement, right, by just voting it. So we will answer that question today. And there's some really interesting matroids, it turns out, that are not F-representable, which basically is very useful, because basically one of today's lecture might be called Matroids Are Flexible and Powerful and Weird. So in other words, it might mean that you can do a lot of stuff with matroids, even within the matrix case. But once you go outside of the matrix case, then it gets even a little bit stranger. So just a couple of more definitions, because we need these. We need to be clear on these today. So the notion of a closed set or a flat or a subspace of a matroid is if it's the case that anytime you add anything, you've got a set and it's considered closed if you add anything to the set and the rank increases. So you could think of this as sort of like a subspace, right, in a linear space. So you add all of the vectors and everything. Every time you've added a vector, you've left the subspace because you've increased the rank by 1. And there's a definition, there's a notion of a hyperplane, which is a flat of almost maximal rank. It's basically the rank of the matroid minus 1. So that's the so if you're in 3-dimensional space, a hyperplane is a plane, right? If you're in 4-dimensional space, a hyperplane is a 3 space. And here, if you're in a matroid, which is again a combinatorial geometry, because a lot of this stuff came from geometry. If you're in a matroid, basically a pen-maximal flat is a hyperplane, and I just invented that word, so that word doesn't really exist. So don't look it up. All right, so the notion of a closure. So you can essentially take a set and close it by essentially adding stuff that doesn't increase the rank. And then, of course, the span of a flat is equal to the flat itself. And there's a notion of a circuit or a cycle if it's inclusion-wise minimal dependent. So that basically means that a cycle is such that if you remove any element, it's no longer dependent. So, and then lastly, the notion of a spanning set. So a spanning set is a set whose rank is equal to the rank of the matroid. And if you have a particular subset like Y, X, and X is a subset of Y, X is spanning Y if it's the case that the ranks are the same. Ranks of X and Y are the same. And here's the spanning set of a matroid. So a base, then you can say it's like a minimal spanning set, right? Because if you can add stuff and you'll still be spanning to a base, because the rank's not going to increase. But if you've got a base, it's a minimally independent set. So, a minimally non-dependent set. So as soon as you remove an element, you're going to decrease the rank. A couple of other facts. V is always trivially spanning, right? And this leads to the spanning tree of the graph. So this is all review, okay? So actually, this is a review too, but let me just, I modified this slide a little bit so that hopefully it's a little bit clear, because we want to talk a little bit about the dual of a matroid, because this is it's really neat, I think. So let's say that we're starting with a matroid. Actually, before we do that, are there any questions? Does anybody have any questions about the review? Yeah, Scott.
So you said that there are some matroids that are not F-representative, so that basically they don't correspond to the matrix.
Yes.
Right? So how far is our intuition about matrices, how far can that extend to matroids? We only extend that intuition about matrices to F-representable matroids?
Yes. That's beyond that. It's and that's really important, I think, personally, because if it was the case that matroids and matrices were the same, namely all matroids were F-representable, I think it would have made matroids a little bit less interesting, because it means that these abstract properties were sort of just not really generalizing at all. They were just basically describing a certain property of a set of matrices over some field. But the fact that there are, and this is actually something that Whitney himself discovered back in 1935. He gave an example of non-representable matroids. Just the fact that he discovered that actually was one of the things that made the paper very powerful and very forth. I mean, I think it's an amazing paper. I mean, it's online. You can go and look at it. The submodular inequality is sitting there, right, in plain sight. I mean, there it is in 1935, before anybody realized how important that was. But let's talk a little bit about the dual of a matroid, because this sort of tells you, I think this gives a little bit of a taste of how flexible matroids are. So first of all, we're going to define the dual matroid by saying, well, we start with a matroid M. And a dual of a matroid, first of all, or is defined, I should say, not can be, is defined. The dual matroid is defined on the same ground set, but it uses a very different set of independent sets, I star. Okay? And so basically what we're doing is just the same ground set, right? Just make sure that's clear. And all we're doing is we're changing the independent sets. And the independent sets in the dual matroid are those sets A, such that A's complement is spanning in the original matroid. So what does that mean? It means that a set A is independent in the dual if when you remove it from the ground set, you have not disturbed the rank, that the rank stays the same. And that's basically this definition here. So it's all A, subset of V, such that when you remove A from V, the rank stays the same as the rank of the matroid. And now you might think, wow, is that a matroid? That seems really strange, because basically you're saying its complement is spanning the original matroid, but that's what we want to see, and what we're going to prove. So a set is independent. This is just sort of restating it again, in case it's not clear. A set is independent in the dual if its complement is spanning in M, right? So yet another way of saying it, here's a nice way of saying it. So the residual, so the complement of A must contain a base, right? Because if you're spanning, that means that some subset of you is a base. Or it might mean that you are a base, right? But it might also mean that you contain a base. So either you contain a base or you are a base. Now, just from the definition, we note that if we take the dual of the dual, so M star is the dual of the matroid M, and M star star is the dual of the dual, which just gets back to M. Okay. So this gives us some interesting sets of things. So let's look at this for a minute. So in general, so when you have a matroid, the smallest spanning sets are bases, right? So as soon as you're not a base, as soon as you take any element away from a base, you're no longer spanning. Now, in the dual matroid, okay, so let's take these guys, okay? So these are the things in the dual matroid that must be spanning. So in other words, for I to be independent in the dual matroid, V except for I needs to be spanning, right? And to make V except for I as small as possible, right? That corresponds to a base, right? That corresponds to a base in the original matroid. But making V except for I as small as possible means making I as big as possible, right? Because basically any subsequent removal from V except for I would no longer be spanning. That's a base. So therefore, any addition to I would no longer be independent in the dual. And so basically that means that the complements of bases in the primal matroid are bases in the dual matroid. Okay. Now, does everybody see that? So in fact, we even have a theorem that states this, that, this is sort of, I think just looking at the definition, it's fairly clear, but basically, let's say you have a matroid, M, and let's say that B of M is defined as the basis of M, script B of M. And let's define this strange function called B star of M. Okay, so B star of M is all sets B complement such that B is a base of the original matroid. So basically you take all bases of the original matroid and you complement it and then you stick it into a set of sets. So complements of bases. So then what that's saying is that B star of M is the set of bases of the dual matroid M star. Or another way of saying that is that B star M, the strange B star operator on the matroid M, is equal to the bases of the dual matroid. Okay. Any question on that? Now let me just pause for a second to let everybody digest it, and then I will move on. Because when there are no questions, it means that you're digesting. I can feel the acid dissolving these concepts. Okay. So this is going to be really cool, I think. I think you really like this. So let's just do a little bit more terminology. So basically, B star of M are the bases of the dual, right, or B of M star. But the bases of the dual are called the co-bases of the original matroid. Okay. The circuits of the dual are called the co-circuits of the primal. Unsurprisingly, the hyperplanes, remember what a hyperplane is? It's a closed set that has rank one less than the rank of the matroid. It's a hyperplane. The hyperplanes of the dual are the co-hyperplanes of M. And the independent sets of M of the dual are the co-independent sets of M. And the spanning sets of the dual are the co-spanning sets, and so on and so forth. Okay, so everybody get that. So basically what this gives us is a language that allows us very easily to talk about a set having a certain property in the dual without having to say the hyperplane of the dual. You can just say the co-hyperplane. It's a co-hyperplane. It's a syllabic reduction. It's a syllabic compression strategy for talking about matroids. But where it gets more interesting is in this theorem from Oxley. This is one of our books. So basically it's saying that X is some subset, right? You've got some matroid, and X is some subset. So we're saying that X is independent in M if and only if its complement is co-spanning in M, or namely it's spanning in M star. Now why is that true? Anyone want to take a shot at it for a quick proof? This one should be a one-sentence proof. In fact, it's a two-word proof. By definition. Thank you very much. Exactly. This is just a definition of the independent sets of a matroid. Or you can always switch a matroid and its dual, right? You can say, for example, X is independent in M star if its complement is co-spanning in M. Or spanning in M, right? Now, X is spanning in M if and only if its complement is co-independent in M, or namely it's independent. So basically, a spanning set, right? What does a spanning set mean? Well, you could say you could have a base is spanning, or any superset of a base. So if it's a graphic matroid, you can have a spanning tree, or any spanning tree, which is a set of edges. Remember, when we're talking about graphic matroids, the ground elements are the edges. So you can have a spanning tree comprised of the edges that create that spanning tree, or any superset of that spanning tree. So any superset of a spanning tree is such that its complement is independent in the dual. So that's going to lead to some, as you'll see very soon, some really bizarre notions of independent sets when you look at the graphic description of them. This sounds so funny when you talk about graphic. But in any event, now if X is a hyperplane in the primal, then that's a hyperplane if and only if the complement is a co-circuit in M, or what's called, or circuit in the dual. Okay. So if you take the complement of a hyperplane, remember a hyperplane is this closed set of rank one less than the rank of the matroid, then its complement is a circuit. So that sounds also very strange, potentially. And then if it's a circuit in M, then its complement is the hyperplane in the dual. I mean, that's not so surprising. So anyway, these are kind of obviously, these first two go together, and these second two go together, right? So these are almost dual statements of each other. Now this is where it gets really fun. So we have, one of the nice things about graphic matroids, or cycle matroids, or namely matroids which comprise ground sets consisting of the edges of the graph, and where cycles are, circuits are cycles, and are minimal spanning sets are spanning force or spanning trees if the graph is connected, and where spanning sets are basically supersets of a spanning force or spanning tree if the graph is connected, is that one of the nice things about graphic matroids is that it's just really easy to reason about them. And from the perspective of matroids, from the perspective of sort of visualizing matroids and reasoning about matroids and actually using matroids in machine learning, because after all, this is a class supposedly about submodularity machine learning, we would like ultimately to use matroids somehow in machine learning, which I will talk about once we've talked about constrained submodular optimization. But one of the nice things about graphic matroids is that they're just easy to work with. They're easy to visualize, they're easy to represent on a computer, they're easy to query. What wouldn't be easy to represent in a matroid is having essentially a large list of sets, or set of sets consisting of the independent sets. That wouldn't be a viable representation of a matroid. Is it independent? Well, you search through this, this exponentially large set of independent sets. That's not viable. However, if you have a graphic representation of a matroid, it is easy because you can see whether if it's independent, see if there's a cycle. And there are fast algorithms that work on graphs that test whether or not a particular set of edges contains a cycle. Okay. Now, unfortunately, or fortunately, depending on how you look at it, not all graphic matroids are matric, and not all matric matroids are matroids, or general matroids. I mean, and so therefore it sort of renders the graphic matroids perhaps less complete. I mean, they're not, you don't span all matroids just when the graphic matroids. But what the concept of duality does is it sort of extends the set of matroids that can be usefully described with a graph, and it leaves the notion of a graphic matroid without actually leaving the notion of efficient querying and efficient independent set representation. And that's thanks to the dual. And in general, the dual, even if we leave the graphic matroid case, it just demonstrates how powerful the matroids are. So let's see how that works. So in a cycle matroid or a graphic matroid, a spanning set is any set of edges that are incident to all nodes, right? Like it's a superset of a spanning forest, as we've said. And a minimal spanning set is a spanning tree if the graph is connected. And circuits, I've already said this. Circuits have nice visual interpretations. They're cycles in a graph. It's very easy to see. Now, a cut is also something that's sort of visually useful in a matroid. So what is a cut? So let's say you've got some graph, and a cut is a set of edges. Now, the original graph, has some number of connected components, right? If it's fully connected graph, if it has one connected component, then basically everything's connected. But the definition of a cut is a subset of edges such that when you remove them from the graph, you've increased strictly the number of connected components. Okay. That doesn't mean that it's a minimal cut, because our notion of a cut, like usually when we write a cut, like we have some graph and we just remove this, we cut through the graph, and basically if we've left a gap in any one of these guys and left a gap anywhere here, then there's going to be an edge that goes through there. That would be a minimal cut. And what a minimal cut is basically one such that any subset of the cut is no longer a cut. So if we remove any of the edges, is no longer a cut. So the first case can consist of minimal cuts and non-minimal cuts. So non-minimal cuts are ones, the removal of some edges of which don't render the thing no longer a cut. And a minimal cut is one that isn't the case. Now a cocycle, or what's called, a cocircuit in a graphic matrix is called a cocycle, right? Which is this thing down here. It turns out that a cocycle, strangely enough, is going to be a minimal cut in the graph. So in some sense, the cuts define a matroid, but via the cycles. And therefore, a cocycle matroid, as you will soon come to perhaps agree is a reasonable thing to do, is sometimes called a cut matroid. Although it's not that frequently called a cut matroid, because in this particular case, it's the cocycles that are defined by the minimal cuts. And in general, all dependent sets, basically sets that contain a cycle in the dual matroid, or namely in the dual graphic matroid, are cuts, not necessarily minimal. So in other words, a dependent set in the dual graphic matroid is either a cut or contains a cut, or a non-minimal cut. So let's do an example to show you how crazy these things are. So here's the definition of the dual matroid, and here's a graph. Okay. So we know that in the primal, any base is going to be a spanning tree. This is a connected graph, so we can talk about spanning trees here. And there are a bunch of spanning trees, and since there are 8 nodes, all spanning trees have size 7, right? There are 12 edges. Spanning trees have size 7. There's 8 nodes. Okay. And so that basically means that anything that's spanning, so anything that you remove from this graph that leaves either a spanning tree or a superset of a spanning tree is going to be independent in the dual. And moreover, anything that corresponds to a cut or a superset of a cut is going to be dependent in the dual. And interestingly enough, as you might not be surprised to realize, if you remove a cut or a superset of a cut, in the complement of that cut or the superset, is it possible to have a spanning tree anymore? No, all spanning sets are rendered impossible because you've removed edges corresponding to a cut or a superset of a cut. And by definition, by removing edges corresponding to a cut, you've increased the number of connected components. And by increasing the number of connected components, you've removed edges, so now there's more than one connected component. There's no way of bridging the gap between the new components that have been created by removing the cut edges, or the superset of the cut edges. Does that make any sense? I think everything I said was correct, I hope. You can rewind on YouTube and mail me if what I said is not correct. So I'm sure someday, 20 years from now, I'm going to get this mail saying, back in 2014, what you said was not correct. And I'll say, well, I was young then. Now, in 20 years, I won't be anymore. All right, so let's go through this. So on the left-hand side, we've got edges corresponding to subsets in the primal, which are the red edges. On the right-hand side, we've got edges corresponding to subsets of the dual. And it's always going to be the case that the red edges on the left and the blue edges plus the right comprise all of the edges. So we're just basically partitioning the edges. So on the left now, we've got a minimal spanning set, which is a spanning tree. And so therefore, it's base, and it's maximally independent. You can see it's a tree. On the right-hand side, we've got a maximally independent set in M star. Why? Because basically, if we were to add any other edges on the right-hand side, the complement of the right-hand side would no longer be spanning, right? So in general, just think of these edges as A up here, right? So these are these independent sets. The blue edges are sets in the dual, or potentially independent sets of the dual. And we're trying to see whether or not, for example, A is in script I star. Right, and put a question mark by the containment. In this particular case, it is, because when you take the complement of the blue edges, namely the red edges, it's spanning. It's almost not spanning. Right. How about this one? On the right-hand side, we've got these 5 blue edges. If we take the complement, we get the red edges. Now, the red edges are independent, right? But it's not sufficient for it to be independent for the blue edges to be independent in the dual. It has to be the case that the red edges are spanning. And in fact, the red edges are still minimally spanning. And so that basically means that the blue edges correspond to an independent set in the dual, even though there's a cycle. Right? So there's a cycle in the dual. It's okay. It's independent in the dual matroid. So it's like I said, the type of independent sets are totally different in the dual matroid than in the primal matroid. This is, moreover, not only is it independent, but it's a base. Why? Because we said that bases are complements of each other. And since on the left-hand side we've got a spanning tree, on the right-hand side we've got spanning set in the dual. Right? Does anyone want to make a modification to this? So this is a base, meaning it's maximally independent. The other thing to note is that the number of red edges is 7. The number of blue edges is 5. So the rank of the primal is 7, and the rank of the dual is 5. And in general, when you have a primal and a dual matroid, the ranks of the two matroids summed together is equal to the ground set size. That makes sense because the bases are complements of each other. Okay, so let's move forward. Here's an example of, we've got an independent set on the left-hand side, right? It's independent, but it's not spanning, right? Why? Because it's not a spanning tree, because we've got, this group here is not connected with this group here, right? And then if you take the complement of the red edges, we've got the blue edges. So the blue edges, since the complement of the blue, which is the red, is not spanning, the blue edges can't be independent. So there has to be a circuit in the dual. Now notice that the right-hand side, there's a circuit, but there's no graph cycle, right? Because in the dual, it's not graph cycles that correspond to circuits in the dual matroid. What is it that corresponds to circuits in the dual matroid? Cuts. And where's the cut? Right, that's easy. What is it? Well, all it needs to do is contain a minimal cut. Someone said 2746. But I don't think that's correct. So it has to be a cut. So what if we were to take these guys? Right? That's a cut, right? The blue edges contain a minimal cut, or the blue edges are cut. Basically, if we remove the blue edges, if we remove all of the blue edges, how many connected components we have? Let's remove all of the blue edges and color the different connected components. So we've got, at least try to do that. So we have this connected component, that's one. Actually, this is one connected component. And then the other connected component is this one. So if we remove the blue edges, which, by the way, happens to correspond precisely to the red edges on the left. So that's not surprising at all, is it? So the two connected components correspond to the edge-induced graph on the left. Okay. Let's see a couple more examples. So on the left-hand side, we're spanning in the original, in the prime matroid. Is it a base? No, it's got cycles in it. So it's a dependent, it's a spanning dependent set. And so that basically means the left-hand side contains a spanning tree. But it's spanning, so that means it must mean that its complement is independent. But because it's, so it's spanning, it's independent. The blue edges are independent in M star, but it doesn't contain a cut, right? And why is that? So this looks like what might be seen as an independent set. So sometimes in the dual matroid, independent sets are independent. But why does it not? I mean, obviously it doesn't contain a cut. If we remove the blue edges, what we're left with is the red edges, which contain a spanning tree. So therefore, there's still only one connected component. We haven't increased the number of connected components. So it's independent. So there's no cut. Any questions on this one? On the left-hand side, we've got an independent set, but it's not spanning. Okay, so that basically means since it's not spanning, then in the dual case, we must have a dependent set. But is it a minimal cut? It's not a minimal cut. So remember, a minimal cut is the dual of a hyperplane on the left-hand side. Is the left-hand side a hyperplane? So remember, a hyperplane is a closed set. Hyperplane is closed of rank 1 less than the rank of the matroid. Is this thing a closed set? Are the red edges a closed set? How would we close it? Remember, to close it, we have to add all edges that don't increase the rank. So if I add this edge, would it increase the rank? It would, right? Because now I can span. Now I've created it. So in fact, that's a spanning tree, right? So now I have increased the rank. So that's going to increase the rank. That doesn't close it. Anything that connects these two components is going to increase the rank. That's going to increase the rank. All these guys are going to increase the rank. The only thing that's not going to increase the rank is if I add this edge. It creates a cycle, doesn't increase the rank, it closes the set. So that's a closed set. If I were to remove then this blue edge, like, if this guy was gone, would that be a minimal cut? Yes, because it cuts this stuff out. It cuts 4, 6 away from the remainder of the nodes. Maybe even that's the next example. In fact, that's the next example. So here's the closed of the set. It's a hyperplane, so the left is a hyperplane, and on the right is a cycle. In fact, it's a minimally dependent set. I mean, so like I said, the dual matroid is very, very different things. This is a cycle in the dual, which corresponds to a minimal cut. And here's one other example. So it's a hyperplane in the primal, because it's a closed set of rank 1 less than the rank of the matroid. And on the right-hand side, we've got a cycle in the dual. So these 3 edges correspond to a cycle, which is a minimal cut. So cycles can have very, very different behavior. So imagine now defining a matroid using the dual of a graphic matroid. You can have sets of independent sets that are very, very different. than what one would imagine in the primal. But on the other hand, detecting cuts is actually a computational feasible thing to do. It's not so difficult, right? So it makes dual matroids potentially extraordinarily applicable. So let's first of all prove that the dual of a matroid is indeed, in fact, a matroid. Okay, so let's just define the dual. Oh, wait, before I do that, hold on. Time out. Any questions? I have to remember to ask if there are any questions, because I have to give you an opportunity not to ask any. Oh, good. Great question. I already know it's good, because you're asking one. Yep.
Yeah, when you say this is hyperplane, what's the intuition behind saying that it's a hyperplane?
Sorry, what's the intuition? Why it's a hyperplane? Okay, so in general, when you're in like let's say you're in Euclidean space, a Euclidean geometry of like Rn. So any hyperplane is a subspace of rank of dimension 1 less than n, right? It's a dimension. It's a subspace of dimension n minus 1, right? And a matroid is sort of is an abstract notion of a geometry. In fact, it's a particular type of projective geometry, which is a topic which we're not going to have a chance to get much into. But a lot of the terminology from matroids comes from the field of projective geometry and mathematics, and so therefore hyperplanes, which are these, in some sense, the dimensionality of Euclidean space, I mean, you have n dimensions to span. In a matroid, you have the rank of the matroid dimensions to span, right? So a hyperplane is just basically a closed set, with like a subspace of dimension 1 less than the rank of the matroid. Yep.
So I don't quite understand the cut on a graph. Sorry, this is kind of basic. So the definition of cut is that the removal of a set of edges increases the number of connected components.
That's right.
So I don't understand how if you remove an edge, it can increase the number of connected components.
Yeah, this is something that often is. It may be that you need to make sure that what does a connected component mean, and this is a terminology. It's a standard graph theoretic terminology. So basically, in a graph, if a graph is connected, you have one connected component. If a graph is disconnected, you have 2 or more connected components. Right? So each component of a graph is connected, but between these components, they're not connected. So you have 2 connected components. That's the linguistic idea of connected components. So in the original graph, it's connected, which means that there's one connected component. Okay, so in the original graph, basically all of these edges, all 12 of these edges together, that's one connected component, which basically means we don't have to talk about spanning force, we talk about spanning trees and stuff like that. But you can see that if we remove the blue edges, which conveniently, we happen to have the complement. Basically, the residual edges correspond to the left edges on the left side, the red edges on the left. We can see that if we only had these red edges, there would be 2 connected components. Namely, one component would be, I'm going to highlight this in yellow. There's one component of the graph, and the other component I'm going to highlight in green. There's the other component. So that now we have 2 connected components, the green connected component and the yellow connected component. Okay, that's just the graph theory. I mean, it's a little bit confusing, but that's what you use in graph theory. Okay. So you see now how if you remove these edges, you've increased the number of connected components from 1, in this case, to 2. Okay, so let's prove that the dual is a matroid, if there are no other questions. Any other questions? Okay. So first of all, we're defining the dual as we've defined. Basically, it's saying that the independent sets are such that the complement are spanning in the primal. So if it's clear that the empty set is in I prime, because why? Because if you remove nothing, it's going to be spanning, right? And this by the way should be script I. No matter how many typos I remove before this class, I still find more typos. So the empty set is in the independent set because the removal of nothing is spanning, right? And then the subclusiveness, the downclosedness. So let's say that J is a member of the independent set of the dual, independent sets of the dual, and I is a subset of J. And by the way, we're going to get used to I being subsets of J because we're going to use that a lot in this lecture. So in general, I is going to be a subset of J. Or actually, wait, let me take that back. Either I is going to be a subset of J, or the size of I is going to be less than the size of A, but not necessarily a subset. But in general, J is going to be bigger in some fashion. So let me say, don't get confused about the various ways in which I and J are related. In this particular case, there's a subset. And so I is a subset of J. J is definitely independent. So therefore, we're going to say that I is independent because if it's the case that if we remove J and it's spanning in the primal, then if we remove less, then it's of course also going to be spanning, right? If you take a superset of a spanning set, you're still going to be spanning. And so therefore, I is independent as well. So the main thing we have to do, and the main work, has to be the sort of exchange property. So now what we're going to do is we're going to use I and J in this size case. So I and J are both independent sets, or both members of I prime. We know it's an independent system because it's empty set containing and subclusive. And we have two independent sets, I and J, where the size of I is less than J, and they're not necessarily subsets. And we need to show that basically we can take a member of J, so there's some guy in J we can add to I, such that I plus that member, namely V, is still a member of this. And to show that, basically we need to make sure that if we remove, so we know that V except for I is spanning in the primal, right? So we need to make sure that there exists a member of J that if we remove it from V except for I, namely V except for I except for V, which is also equal to this, that continues to be spanning. It doesn't have to mean that all members of J has that property. There has to exist at least one in J that has that property. So removing from this doesn't make this non-spanning. Okay, so we know that J is independent, right? And since J is independent, we know that this is spanning in the primal. And by it being spanning in the primal, must mean that it is either a base or it contains some base. So let's say that B is that base, or is a base contained in this spanning set V is that for J. Right? So B is a base, and this is a spanning set. V except for J is a spanning set in M. And since I is also independent, right? We know that V except for I is spanning in the primal, and so therefore it also contains a base, and let's just call it B prime. Okay? So B is the base in the spanning set V except for J in the primal, and B prime is the base in the spanning set V except for I in the primal. Now, we know that B except for I is a subset of V except for I. Why? Because V is the ground set, and B is a subset of the ground set. Anything that's a subset of the ground set. And so if we remove I from B, that's going to be no greater than removing I from the ground set. And we also know that B is a base, right? And we know that we have the subclusive property of already. And so if we remove anything, that's also going to be independent. So any subset of B, any subset of the base is still going to be independent. In particular, if we remove I from B, that's going to be independent. Okay? So then it turns out, therefore, that we can choose this base B prime such that B prime is sandwiched between B except for I and V except for I. Okay? So we're just going to choose the particular base B prime to have that property. Okay, so we're going to use this then. We're going to use this, all this stuff. Okay. Now, the other thing we note is that B and J are disjoint. Why is B and J just B and J is disjoint? Because we've chosen B to be a subset of the complement of J. Okay. So since B and J are disjoint, we have that B except for I and J except for I are also disjoint, because if we remove stuff from two disjoint sets, the residuals are still going to be disjoint, right? And also, when we take the intersection of B and I, that's going to be a subset of I except for J. Now why is that? Because basically, B and J are disjoint, right? So this guy here and this guy here are disjoint, right? And so if we intersect B with I, that's still going to be disjoint with J. So therefore, it has to be anything in I and B cannot be in J, because B and I is disjoint with J. So therefore, it's a subset of I except for J. We've not removed anything from the intersection of B and I by removing J from I. Yep.
Wait, how do you know there's a B prime and sandwich between B minus I and B minus J I?
Well, these timeouts don't ruin anything. Okay, so let's get back to the question. So the question is, how is it possible to choose this B prime such that this statement is true? So first of all, B except for B and B prime are both bases in the matroid M, right? This is just in case it's not clear. So we've got a matroid M, and we've chosen two bases which have the same size. And then when we've removed stuff from B, as we've done here, so B except for I has removed stuff from B, right? So we've removed a set. So we have something which is a subset of a base, which is independent. But we can always then add stuff to that subset of B and keep it independent, but it will be a base of this other thing. And that's basically because of the matroid property in M, because it's basically a base in the matroid M. Right? We're trying to prove that the dual of the matroid, M star, is a matroid, but we have, and we can use that M is already a matroid, and so therefore we can add stuff to the subset of a base, B except for I, and we keep adding stuff, and we'll keep as long as B prime is bigger than B except for I until we've constructed B prime, in which case we're going to be bigger than B except for I and smaller than B except for I.
Don't two bases of the matroid have the same cardinality?
Yes, so two bases of the matroid have the same cardinality. And that's exactly what I'm saying here, is that when you look at this statement, the idea is that you start up with this guy, which is going to have smaller cardinality. So that's not, once we've removed I, it might be a base already, but maybe it's not. The point is, it's going to remove some stuff from B. It's still going to be independent, because if you remove stuff from a base, you're independent. But thanks to the matroid property, right, you need essentially to be able to reconstruct a base of this subset, V except for I. Right? And so how do you get a base of that subset? Well, you can start with any independent set, which is a subset, because B except for I is definitely a subset of V except for I. But the matroid property says you can always find some other element that can be added. It's always going to be a subset of V except for I, and we keep doing that up until B prime and B have the same cardinality. Okay. And that's the matroid property in M. That's what all this stuff is, in M of M. It's all there. Okay, now what we're going to claim is that J except for I, namely the stuff that's in J but not in I, is not a subset of B prime. And what that's going to allow us to do, by not being a subset of B prime, it means that there's something we can take from B prime and add it into I, which renders the complement still spanning. Okay. Now, first of all, we need to prove why this is true. Okay, so why is this true? So first of all, let's assume that J except for I is a subset of B prime. Okay, so if that's true, so then first of all we have this. So B is equal to B B intersect I plus B except for I, right? Well, that's just basically that's partitioning B into two sets: that which intersects I, and that which is in B but not in I. So then this and this follows. This next line follows from this. Let's erase this a little bit. Because B intersect I is a subset or equal to I except for j, the size of B intersect I is going to be less than or equal to the size of I except for j, right? Now, okay, everybody see that? But we've also, by assumption, we've assumed that the size of j is greater than the size of I, right? So therefore, that means that this is a strict inequality here, because what's in I naught in j is going to be strictly less than what's in j naught in I. And if you would like a picture of that, you can sort of think of it as like, let's say that here's I, and here's j. Right? And so what's in I naught in j is this stuff, and what's in j naught in I is this stuff up here. Okay? The intersection is the same, of course. And so therefore, that's a strict inequality right here. Now, we've got this last guy, okay? So we have that j except for I is less than or equal to b prime by assumption, which comes from, hopefully from, where did we get it from? From this, right? So we've got this guy by assumption. And we have b except for I less than b, which is where we're using this property. So we do need this. But if we have both of those things, so we failed, then basically the union of these things is going to be less than or equal to b prime. But since these things are disjoint, j and b are disjoint, we have that the sum of these two things are less than or equal to b prime. The sums of the size of the things are less than or equal to the size of b prime, which really is this thing right here. So that's what I mean by typos. Okay? But that leads to a contradiction, because we said that both b and b prime are bases. So it's a contradiction because now we're saying that b, which is a base, and b prime is a base, and we have this strict inequality, and so that's a contradiction. So therefore, we must have that this is true. That j except for I is not a subset of b prime, which means that there's some guy in b prime, or there's some guy in j except for I, which is not a member of b prime. Right? So there's somebody in j, not in I, that's not a member of the base that we've got. So if we were to add it to I, so obviously v is in j, right? Because we took it from j except for I. So we took it from j. So I plus v is such that this guy is still a superset of b prime. Why? Because when we removed v from j, we haven't removed it from b prime. And so since it's a superset of some base, it's still spanning. And so therefore it's independent. Okay? So the theorem is proven. Okay, so any other questions?
I was thinking that this problem could probably be proved by, in a simpler way, using
Very likely.
using the exchange property of the base of a matrix.
It's very possible. Yes. Would you like to do that on a problem set?
I think it could be proved.
Yeah, very possibly. Yeah. Certainly by using, for example, like the definition of the complement of the bases are bases. That would be an easy way of doing it. Okay. Now here's a notion of matroid duals and representability. So basically we have this F representable matroid. It turns out now, does the dual allow us to leave the space of F representable matroids? Because we said that, we sort of hinted at, we didn't actually give an example yet of, but we hinted at that basically not all F representable matroids, not all matroids are necessarily F representable. But it turns out that taking the dual of a matroid doesn't leave the space of F representable matroids. But on the other hand, if we actually looked at the set of graphic matroids, then the dual is not necessarily graphic. So the concept of dual matroid really does give us more power, more matroid power, but without really giving us any sort of computational concerns, because we can use notions of cuts on graphs and easy graph algorithms, for example, to represent sets of independent sets, yet we don't actually have a graphic matroid. So this potentially is very powerful. This is what I was saying at the beginning.
Can you give us an example of this scenario?
Of M star not being graphic? Yeah, it's a little bit complicated, but if you take, for example, like the dual of a complete bipartite graph, it's not graphic, turns out. I'm not, like the complete bipartite graph would be something like this on 3 nodes. You take the dual of this, and you have to show it. I'm not. You'd have to go through the example.
But the dual still have the nodes and edges, right?
I'm sorry?
The dual still have nodes and edges. It might not
Yeah.
be about, but anything with nodes and edges can be defined as a graph, right?
But the thing is it a graphic matroid for some graph? It doesn't have to be the same graph. And is it graphic? Is it representable with some graph? Right? So the ground set has to be the same. There has to be some edge set, and it has to be isomorphic to the dual, in terms of that you can prove that there are examples of dual graphic matroids for which there's no graphic matroid that's isomorphic to that dual. I'm not sure about this bipartite example, but I know there are examples. But what I wanted to do is talk about the rank function of the dual. So the rank function is given in this way. So the first thing to see about the rank function is that we can see it's submodular. Why? Well, we know that the rank function of the primal is submodular, which is this. Taking the submodular function of the complement preserves submodularity. And then adding a modular function to a submodular function preserves submodularity, and subtracting off a constant preserves submodularity. So therefore, this rank function is going to be submodular. Now, is it a rank function? Well, it's obviously integral, right? Because it's adding and subtracting integral quantities. Is it non-negative? Well, what we can do is we can see that this quantity here is greater than this quantity. And we get that from basically the size of x plus the rank in the primal of the complement is going to be greater than or equal to the rank of x, because the rank is always going to be less than the size of x, plus the rank in the primal of the complement. And then we get that that's greater than or equal to the rank of v. And we get that last inequality, this one here, thanks to the submodularity of the rank, because the rank of x plus the rank of the complement is greater than or equal to the rank of the union plus the rank of the intersection, and the intersection in this case is the empty set. So the last thing we need is the monotone non-decreasing, but that follows right away, because basically when we add an element to x in this guy, well, the size of x is going to increase by 1. This guy, the constant, is going to stay a constant, and the rank of the complement is either going to decrease by 0 or decrease by 1. Right? So we have monotone non-decreasing and, for that matter, unit increase, because of the fact that either we're increasing by 1 or increasing by 0, depending on what happens to the rank in the primal. So therefore, it's a rank function of some matroid. Right? The question is it the rank function of the dual matroid? And you can actually see this right away, because we can say that a set is independent in this. Let's just define this matroid by this rank function. We have the ground set and this rank function. Remember, we said that we can define a matroid by giving a ground set and a rank function. So here's a matroid, and a set is independent if and only if the rank, according to this function, is equal to x, which is equal to that, right? But when we cancel out stuff, we cancel out this and this. Basically, that happens whenever this is true. Or in other words, whenever the complement of x is spanning in the primal. So therefore, this is the rank function of the dual. Okay. Any questions about the rank function of the dual? Okay, so we're going to spend a little bit of time. I was hoping to get to matroid and greedy today, but I don't know if that's going to happen. But unless you want to stay late, raise your hand if you'd like to stay late and finish our intended slides for today. Well, since you're all raising your hands, I will continue. So let's. So the notion of matroid restriction and deletion is important. So basically, the idea of we've got a matroid, and we can choose any set Y, and we define basically this set of sets, which are subsets of Y but independent. So that actually then is going to define another matroid. Okay, and it's going to have a rank function. Basically, it's going to have a matroid with rank, the rank of Y, whatever that rank is. And this is just essentially called a matroid restriction, or it's a restriction of M to Y. And sometimes you can write it like this. And when you do this a lot, then you write it as M vertical bar Y. You're restricting it to Y. Now this is actually something that's really important because we do this a lot with submodular functions even. In fact, this is something that we saw that we did with polymatroid functions when we were defining a graph cut. We were restricting it to pairs and summing them up together. So it's really, in some sense, a bunch of restrictions. And then deletions is sort of like restricting to a complement set. Question?
Is the restriction on IY?
Sorry, say again.
Apart from the given statement ZZ subset Y that belong to Y, is there any other restriction on IY or how we?
I can't. Sorry, what are you saying? I can't hear what you're saying.
Is there any other restriction on IY based upon how or which subsets we choose for IY from IY?
No, this is any subset. Okay, so basically we're taking any Y. Doesn't matter about Y. We're just defining a restriction to Y. It's still going to be independent, right? Because we're taking two things. We're taking subsets of Y, and it has to be independent in the original matroid. And so you're going to be independent in this new matroid. But it's going to be a matroid. All bases in this new matroid are going to be the same size, right? And the bases are going to be, for example, the size of the maximal independent. It's like the rank of Y, right? The basis is going to be the rank. However big the maximal independent set, which is a subset of Y, is, that's going to be the new rank. That's going to be the size of the new bases. If we restrict to a complement, the complement of X, then that's called a deletion. And what this really corresponds to is when we define Y to this complement set, we're basically defining a set of independent sets that don't intersect X. So we're sort of removing, in some sense, X. And sometimes you write this as in this. In fact, this is a notation that we use a lot in graphs. Like when you have a set of edges and you have a graph G and you say G except for some set A, where A is a set of edges, that basically corresponds to the removal. In fact, that's a notation we even used before when we talked about the number of connected components increasing on the graph by removing a set of edges. So this is just basically using the same notation in a matroid. So that means that when we can either restrict to Y or we delete the complement of Y. That's the same thing. But in either case, the rank function is the same. Basically, we define a rank function on subsets of Y, and the rank function is this. Okay, we just basically take the original rank. Now there's a contraction, which is like a combined operator. It's you're sort of forcibly including a set within every evaluation of the rank function, but then you're sort of deleting the rank of that set. And that's called a contraction. So you're sort of contracting on Z. So basically, what does that mean? Let's just define that. So let's say that Z is any subset. Okay. So Z is any subset of V. It may or may not be independent. Let's say that X is any base of Z. And then what we say is that so we're sort of in some sense removing Z from consideration. And so we can talk about subsets of the complement of Z. And any given subset, say I is independent in the complement, subset of the complement of Z is independent. If it's the case that when we add the base back onto I, it's independent in the original matroid. And so what that means then is that when we we can sort of define the contraction operator. I mean, this is sort of an exercise for you to show, as basically doing this. Okay? We take a given z, then we take the matroid, find the dual, we delete z, and then we take the dual again. And that basically corresponds to the contraction. And then the rank function takes the following form. The rank function is really just like a conditional submodular function on the rank. This is what I mean by the forced inclusion, is by basically evaluating any subset along with z, but then you remove the rank of z, which is like removing, because the rank of z is equal to the rank of x. So it's the same thing. So now let's just define what, again, it means for it to be independent. So if you're choosing a particular I, which is a subset of the complement of z, and x is a base of z, then the notion, this is a rank function, the notion of I being independent is identical to using this definition of the rank is equal to R of I union z is equal to I plus the rank of z, but the rank of z is equal to the size of x because x is a base of z. But we also know that since x is the base of z, in the original matroid, the rank of I union z is equal to the rank of R union x. Since nothing beyond x is going to increase the rank, since x is a base of z. And so this gives us essentially the following. That independent in this contracted matroid corresponds to the rank of I union x equaling the size of I plus the size of x. Okay? Now there's this whole area of matroid minors. And minors are very similar to graph minors. In fact, a matroid minor generalizes the notion of a graph minor. And a matroid minor is any matroid obtained by a series of deletions and contractions. And one of the ways you can show, for example, lack of representability of a particular matroid is by showing that it has a minor which is not represented. And so any matroid whose minor is non-representable is also going to be non-representable. And that's generally what people do. We're not going to prove this, but that's just something to mention. Now, there's a couple of other definitions I want to mention. So there's this notion of matroid intersection and matroid partition, which is where we're going to talk about. But let's first define matroid intersection. So the idea of a matroid intersection is really important. Like you have two different matroids defined on the same ground set, and you're interested in, for example, independent, common independent sets. Like as an example, let's say that we have balls in urns, and we have both color and flavor, and we want basically to choose a set of balls that has all the possible colors, so it has full rank, and has all the possible flavors, where color and flavor may be, completely separate. Like you might have a red ball that's really lemon flavored, and a blue ball which is raspberry flavored, and you might have a green ball which is watermelon flavored, or something. I don't know. You could have all sorts of different mismatched colors and flavors, and therefore they would be independent in both matroids which are independent. Now, the intersection of two matroids is not typically a matroid. But on the other hand, we still might be interested in finding the maximal common independent set. Like another way of thinking about this is, let's say you've got two graphs defined on the same set of nodes, different set of edges, and you want to find the max. You want to find the max set of edges that does not contain a cycle in both graphs. And so what we can do is we can actually define a very interesting construct, which actually, as you'll see in a minute, corresponds to convolution. So those of you familiar with signal processing know the notion of convolution of two signals. This is actually a notion of a convolution of two rank functions. And so what this is basically, this gives us, the convolution of R1 and R2, these two rank functions, evaluated at V, the ground set is defined to be this. And this actually then gives us the size of the maximum common independent set. Now, why is it convolution? Because we can actually define the convolution in general of two submodular functions in this way. So f1 star f2 is the convolution of the two functions evaluated at y is basically equal to this minimization problem. Now, interestingly enough, this minimization problem, if f1 and f2 are both submodular, corresponds to a submodular minimization. So just to evaluate the convolution, you need to perform submodular function minimization. And in fact, we can even see Hall's theorem as convolution. So let's just do this quickly. So we have Hall's theorem again, which basically says the neighbors of x, size of the neighbors of x can't be any smaller than the size of x. And so that's equivalent to this. This is true for all x, which is true which is equivalent to saying that the minimum over x of this has got to be greater than or equal to 0, which is the submodular minimization problem, which we can add v to both sides. It's a constant. Add that to both sides. And we have v minus x is the same as the size of v except for x, which is this. So now we see that essentially what we're doing is we're convolving this submodular function. It's kind of a little bit, yeah, I think we're missing a couple of vertical bars here. Let's zoom in so you can see what I'm doing. So we've got the outer part here, which is evaluated at v, right? You've got this function here, the green function, which is the modular function. It's just the cardinality. And then we've got the size of the neighbors. So that's what we're missing. And so we're convolving this function, which is f1, and this function, which is f2. Now, in this particular case, it turned out to be submodular. So do you think possibly that convolving a submodular and a modular function preserves submodularity? Is that an exercise? Another nice exercise. What do you think? Okay. Hint. Okay. So, matroid union. Matroid union is another way of constructing interesting matroids. And in this particular case, it's nice because it preserves the matroid property. So we've got a set of matroids, and we define the union of the matroids as basically taking the disjoint union of the ground sets. Now, what does disjoint union mean? Is anyone unclear what disjoint union is? So disjoint union basically means that we take the union of the two sets but preserve their identity. So like if I had one set, say 1, 2, and 3, and I wanted to take the disjoint union with, say, the set 1 and 2, that would be equal to the set that sort of treats them as essentially distinct items. So you could, for example, think of each item as having a tag. Like you might have 1, 1, 1, 2, 1, 3, and then 2, 1, 2, 3. So the idea here is that each item in the disjoint union of the set is a tuple of length 2, the first element of which indicates what set originally it came from. The second element is the item in that original set. So you've preserved the original sets, and so therefore you've made the size. When you take the disjoint union of two sets, you're summing the size of the two sets. There is no intersection even if the names are the same. And so the disjoint union of the independent sets are the same. Now the rank function takes this form. It's another form of minimization. The rank function is, first of all, the disjoint union, or the union of matroids is still a matroid, and it has a sort of an interesting looking rank function, which is this, which is another form of minimization. This particular thing, it needs to be clear, is sort of the restriction. This is the rank function defined on the restriction of x, which, remember, it contains these tuples or something. It's the disjoint union. It restricts it to the original set corresponding to that particular matroid, R1. So it's a little bit of an abusive notation. So in some sense, it's the non-disjoint intersection, or something that breaks things back apart. So you do have another exercise, which all of this stuff is going to appear in your homework next one. So to essentially describe what it means to take the union of a matroid and its dual. Okay. Now it turns out, and this is kind of interesting, like we're sort of interested in sort of describing properties of matroids. So we're interested in describing matroids that either have a small number of elements or describing matroids that have small rank. And so it turns out that matroids that have a small number of elements turn out to all be graphic. Namely, all matroids up to and including the 3-element matroids are graphic. So there's only one matroid with 0 elements, and here it is. No edges, right? 0 elements. That was this example from before. Why do we have I1, right? So we need to include that guy in there. There's no other matroid. There's two matroids that have 1 element. It's either this one. So this one basically has the element whose rank is 1, and this one has the element whose rank is 0. Okay. There's 3 elements. There's four 2-element matroids. So here's one where, everything is independent. Here's one where there's a parallel edges. Here's one where you've got 1 loop and 1 guy who's got some rank, and here's one where you got 2 loops. So both of those guys have rank 0. And the rank. So the rank. What's the rank of this matroid? What's the rank of the top matroid? 0. And what's the rank of this matroid? What's the rank of this matroid? Sorry? 0. And what's the rank of this matroid? It's easy, right? Okay, so there's 8 3-element matroids, sort of ordered roughly in increasing rank. I think actually in increasing rank? No. That's not true. Roughly. So this is nice for talking about matroids that have a small number of sets. But what if we have a matroid that has a large number of sets, but that is low rank? So we want to be able to reason about this. So in order to do this, we need to define the notion of an affine matroid. And everybody, I'm assuming, knows what an affinely independent set of vectors is. But just in case, let me review. So we've got an n by m matrix, which is defined over some field. And we've got a subset of the indices corresponding to column vectors. Let's say that S is a subset of size k. And we say that the corresponding vectors are affinely independent if, first of all, there's more than one of them, or more than 0 of them. And if we have essentially a set of coefficients also from the field which are not all 0, and which sum to 0, and which, when we take linear combinations of the corresponding vectors, give us the 0 vector. So basically, one vector is a combination of the other set of vectors where the set of coefficients has to sum to 1. It's another way of looking at it. And if it's not the case that the set is affinely dependent, then it's called affinely independent. And another way of just visualizing affinely independent sets, so we have k, the vectors v1 through vk are affinely independent if it's the case that when you subtract 1 from all the rest, they're linearly independent. And so you have things, for example, like in R2, you've got 3 collinear points are affinely independent, and in R2, if you have any 4 distinct points, then they're affinely dependent. Did I say affinely independent? I meant affinely dependent here. And you have 4 or more non-collinear points are affinely dependent. So an affine matroid is basically one that's defined based on affinely independent vectors. And it turns out that that's a matroid. But what we can do with this is sort of visualize matroids in a geometry based on affine independence. And this gives us a very powerful, like I was saying, gives us a very powerful way of viewing matroids that have low rank, even if they have a large number of sets. So for example, here's a matroid defined on the field of reals. And we're going to let the elements of the matroid be the set of points in R2. Okay, so each point is a ground element. So in this particular case, we have 6 ground elements. We've got 0, 0, which is this guy, 1, 0, which is this guy, and so on and so forth. don't need to write them all out. Now, you might think that how is this going to describe dependence and independence? So we're going to use the notion of affine independence and affine dependence to describe the dependence and independence properties of the matroid. And so here we've plotted these points. And whenever it's the case that we've got collinear points that are affinely dependent, we're going to essentially say that the corresponding elements in the matroid are dependent. So dependent sets, so any dependent sets consist of all subsets with greater than or equal to 4 elements. Okay? Or 3 collinear elements. Now, why do we not, for example, why do we not write a line between these two, say? So those are 2 collinear points, right? But in some sense, if you have 2 points that are collinear, those aren't considered affinely dependent because they're not, right? If you need 3 points that are collinear for them to be affinely dependent. So trivially, we just don't bother to write lines between 2 points, since those lines aren't the ones that correspond to dependent sets necessarily. But whenever there's 3 points in a line, like for example these guys, or these guys, or these guys, we draw the line to indicate the dependence between them. So in other words, it's basically saying that the rank of each one of these green lines I just drew is 2. Right? And what this says is dependent sets consist of all subsets with greater than or equal to 4 elements or 3 collinear elements. So anytime you have 4 elements, because you're in R2, you're going to be affinely independent. But if you have 4 elements, what's the rank of the 4 elements going to be? Sorry? 2. If you have 4 elements? Anyone want to comment on that? So remember, 4 points are affinely dependent. So if you've got 3 points, if you have 3 points, are they affinely independent? They're linearly dependent, but are they affinely independent? So dependent sets consist of all subsets with greater than or equal to 4 elements. So that means that the rank has to be less than 4 if it's 4 elements. So the rank of these four elements are going to be 3. Okay? And in general, when you have a matroid of rank, this doesn't give you, the geometry here is that since we reason in R3 or less, we can't really visualize a matroid whose rank is that high. But on the other hand, we can stick points all over the place. And as long as the rank is not high, we can actually visualize and reason about the independence of a matroid and possibly build a computational model such that we can query low-rank matroids, which can be very useful. So for example, here we have a matroid M of rank m plus 1. Or in general, when we have a matroid of rank m plus 1, as long as m is less than or equal to 3, then a subset, then then the points are dependent if you have 2 points and they're identical, or 3 or more points and they're collinear, or 4 or more points and they're coplanar, or 5 or more points and they're in space. They're there. So it basically means that we can't have a rank. Just naturally, all such points are going to be dependent. So what this says is that the theorem says that any matroid of rank up to 4 can be represented by an affine matroid in R m minus 1. So a matroid of rank 4 can be represented in 3 space. A matroid of rank 2 can be represented in 2 space. Okay, maybe we should pause, or we should stop and see if there are any questions. Okay. No questions? You all want to get out of here. Okay, so I will see you on Wednesday, and if there are any questions, I noticed that there was one question on your homework. Please post it as you did. Thank you very much for posting a question to the discussion board, and I'll try my best to answer them as quickly as possible. So